So let's look at row reduction of linear systems, as the heading is called for this section. Basically, you're using matrices to solve a system of linear equations. It's just sort of introduction to it in a course like this. So a matrix is just a rectangular array of values, and you have like A equals 1, 5, 3, 6, 7, 9, which is your 3-row, 2-column matrix. That's why it's 3 by 2. 3 rows first, column second, so 3 by 2. It's always row followed by column. So the augmented matrix of system is just in brackets A and then a line and B. So you have A equal coefficients of variables from the system and B equals right hand side of equations. So past the equal sign basically when this thing's in standard form. So the system is solved by bringing A, B to, you have identity matrix, which is just given a capital I usually, so it's 1, 1, 1 in a diagonal line. So you have a diagonal of 1s and everything else is 0. S1, S2, and S3 on the right hand side in this 3 by 3 one. And X equals S1, Y equals S1, and Z equals S3, for example. And you have elementary operations are used on A, B. You have constant times row of matrices. Constant times one row of a matrix. Very similar to constant times an equation. So it's basically, the other thing we used it a couple times just as more of give you an idea for this, using the Gauss Jordan method in general on this type of thing. You can swap 2 rows and you can do row I plus C times row J. But yeah, row I plus constant times another row. And that's all, and nothing changes when you do these except for the whatever row it was. And you know, a computer would do only one step at a time, but you can do 2 steps at once, really just for efficiency on paper and stuff to save up paper space and work. As long as you know what you're doing. Final matrix in Gauss Jordan method is in row reduced echelon form. So first entry does not equal 0 and a row is 1, so this is called leading 1. So you have your leading 1 for the first entry. All other entries in the same column of a leading 1 are 0. A leading 1 in a higher row is more to lefts than a leading 1 in lower rows. And finally, rows with all entries equal 0 are lowest in matrix. So we did like an introduction to that with a few examples in the last section on solving those equations using the Gauss Jordan method. We just didn't set it up as properly. And the Gauss method is a different method, sometimes called just Gaussian. So it's bring matrix to upper triangular form and you solve by back substitution. So it's, you know, it's like sort of like how you do things in the older days when you'd solve, but it's still you have upper triangular form at least. So basically you'll have one variable solved immediately and then you'll use that for the next upper one. You go up and up generally because you have the simplest row at the bottom, which is just one variable. And you'll see there's an example in this. But yeah, that's all you have to do. So the big takeaway is that Gauss method is first non-zero entry in a row does not have to be 1. So it can be 0, or no, it doesn't be the first non-zero, right? So it has to be anything other than 0. It can be 1, -1, -5, 10, 20, 1,000, etc. And just entries below leading entry equals 0. So you'll see. But you don't have to have like everything above and below be 0, just below it. That's why it's called upper triangular, because everything below is a 0, below the leading entry in a column. So example, so first find the augmented matrix for each of these systems. So you put zeros with them, so 2x is just 2, -3 minus 3y is just -3, plus z is just 1, and then equals 0 is just 0. x is 1, so then you have nothing for y, so it's 0, minus 2z, so negative 2, and then equal 1, 1, so on. U equals v, v equals w, so we want this in standard form first, so it's u minus v equals 0, v minus w equals 0, so we have 1, negative 1, 0, 0, 0, 1, negative 1, 0, translated from here. But yeah, it's good to have your equations written in a way so it's easier to translate. So we'll skip around a little, get to this. So the given matrix is this gives you a matrix, an augmented matrix for a linear system in the variables x1, x2, x3. Solve for it. It's given to you. This is just an example of how it should look if you get if you solve it and you get exact solution. So the solution is 0, 2, and negative 1. x1 equals 0, x2 equals 2, and x3 equals negative 1. So now solve the linear systems by the Gauss Jordan method, matrix elimination method in these two problems. So 17 is just x1 minus 2x2 equals 1 and negative 2x1 plus 4x2 equals negative 2. Put them in an augmented matrix. So you have 1, negative 2, line 1, negative 2, 4, vertical line, negative 2. So row 2 instead of equation, it's rows now. So row 2 plus 2 times row 1. That makes negative 2 plus 2, so 0, 4, minus 4, 0, and then negative 2 plus 2 is 0. We can't really simplify this any further. Row 1 is as it is. We can't, adding or subtracting any combination of row 2 will just be nothing to row 1. So we let x2 equal s, and then x1 minus 2x2 equals 1, so x1 equals 2x1 plus 1, so substitute in x2 equals s, it's x1 equals 2s plus 1, so the solution is 2s plus 1 and s. X1 equals 2s plus 1 and x2 equals s, so it's a line. Yeah, whenever you write them like this, just as a note, you always do it in order from, like x1, x2, etc., from the lowest number to the greater. That would make sense. Or x, y's, and z. So it's a line, though. So now x minus 2y plus z equals 5, and so on, these equations. So we have a 3 equations and 3 variable system. So first we do row 2 plus 2 times row 1 and row 3 minus row 1. Here you see I'm doing stuff in row 3 and row 2, but nothing in row 1. You don't mess with the row you're doing operations on. So I do row 3 minus row 1. So this is, row 1's left untouched. Same with row 2 plus 2 times row 1. So that, whatever you're messing with, just be careful like that. So row 1 remains unchanged, and we get 0. We get 2 zeros now, so that simplifies things a little. That's how I look at it. I think the best way, really, overall, is to get your zeros quickly, so it gets a 0 or 2 in place, so that then you can continue to simplify down, even if you get sometimes some weird, some quite large numbers. Not even large, but you'll see. It can all be simplified down later with simple multiplication of a fraction. So now in brown we have R1 minus 2R2 and row 3 plus 5 times R2. So R2 is unchanged, and we fix row 1 and row 2. So we got even 2 more zeros. It's starting to look like it, so more. Negative 1 times row 2 is 1 we'll do in 1/16 times row 3. We get a diagonal of 1s now. So we just need to do some more touching up. And row 1 plus 5 times R3 and row 2 plus 3 times R3. You'll get it so we have identity matrix on the left hand side, so it's just diagonal 1s and everything else is 0. And simplify down. So as you can see, it became 13/4, so it's negative 17 plus 65 fourths, so you have to basically do negative 17 times 4 over 4 if you want to do it in your head, or just add them on a calculator or whatever. I'd say keep them in fraction form, so just quickly, you just think negative 17 times 4 divided by 4 basically, so it becomes that over 4, and you add the fractions and you leave it as that. So you get negative 3 fourths, negative 5 fourths, and 13 fourths as your solutions. So x equals negative 3 fourths, y equals negative 5 fourths, and z equals 13 fourths. So that's the solution as shown. And it's an exact point. It's 1 point. That's it. And this, we now solve the same system by the Gaussian elimination procedure. And there's less eliminations needed. So we start the same way as before. We get 2 zeros. This time we only do 1 in the bottom, and then we already have it. As you can see, row 3 plus 5 times row 2. This is good enough. We can go to back substitution now. Well, yeah. Although you could also do 1/16, because that's what you do though. So you have 16z equals 52. So z equals 52 sixteenths, because you divide by 16. So z is equal to 13 fourths as before, 13 fourths. Get the same answers. So what we do is we do negative y plus 3z equals 11 from negative y here, negative 1, plus 3z equals 11. So plug in z and we've solved for y. But first we get in terms of y. So it's y equals 3z minus 11. So it simplifies down to negative 5 fourths. Then x minus 2y plus z equals 5. And we basically solve for x and we plug in y and z to solve for it. Simplify. So we get x equal to negative 3 fourths, and then our solution is the same as before. That's what back substitution looks like. So you spend some less time on the row reduction process, but you spend some time on doing it in a classic method almost of solving by direct substitution, basically. Which is fine. Substitution is good, especially in simpler cases, but for a computer especially, the Gauss Jordan method can be programmed in for a somewhat more complicated equation, a system of equations. And you'll get a solution a lot faster than with a human once you have a code written for it and plug it in correctly. And one last problem. We're given a system of linear equations in 3 variables with the augmented matrix given as here. So for what value of k is there no solution for the system, and is there any value of k for which there are infinitely many solutions? So we just do one row. In my opinion, in my view of it, I think this is the proper way. I mean, the answer is correct. I know that much, because you can plug it back in and get your no solution. If you wanted to check. But no, you do row 3 minus 2 times row 2. And that gives you 1, 0, 1, 1. It's the same, just row 3 becomes 0, 0, and k minus 2, and k minus 4. So k minus 2 equals 0, and k minus 4 does not equal 0 will give you no solutions. So k minus 2 equals 0 means k equals 2. That implies it. So k equals 2 gives no solutions because basically if k, so 2 minus 2 is when k equals 2, so it's 0. 0, 0, 0, and then 2 minus 4 will be negative 2. So 0 does not equal negative 2, so therefore no solution, as we said before. And now, is there any value for infinite solutions? There won't be. So k minus 2 and k minus 4 will have to equal 0, both of them. And that's impossible. The condition is, so k minus 2 does not equal k minus 4 ever. It's pretty simple. What happened is, let's say you add 2 to both sides, you'd have k equal k minus 2. you basically get with 0 to equals something that's not 0. There's no possibility to make k minus 2 equal k minus 4, basically, is what I'm saying. So no value of k will give infinitely many solutions.